want to use the conjugate zeros theorem to find all zeros of a polynomial, and I'm given a polynomial and one complex zero. The conjugate zeros theorem says that if I have a complex root with a non-zero imaginary part, a plus bi, and I have real coefficients, then a minus bi must also be a zero. And there are two different ways I can handle this. I can do the synthetic division. This takes a lot more horizontal space than when we're using real numbers. One plus 3i, negative 3 plus 3i. And then I have to multiply 1 plus 3i times negative 3 plus 3i. And the real part of that will be negative 3 minus 9, so negative 12. And the imaginary part will be negative 9i plus 3i, so minus 6i. I hope I'm not making any mistakes, but there's a lot of room to do so. You can write out that multiplication if you need to. And then I need to multiply 2 minus 6i times 1 plus 3i. And my real part is 2 plus 18. That's a good sign. And my imaginary part is 6i minus 6i. Very good. Okay. And I know that 1 minus 3i must be the conjugate root. So 1 minus 3i, negative 2 plus 6i. Very good. Okay, and then this gives me x minus 2 as a factor, and so 2 is a root. So all of my roots are 2, 1 plus 3i, and 1 minus 3i. The second way to do this is that if I know 1 plus 3i is a root, then I know x minus 1 minus 3i is a factor, and I know that x minus 1 plus 3i is a factor, and I know that I have x plus or minus some other value here that I'm still looking for. So I can multiply these together and then divide the original polynomial by it. So x minus 1 minus 3i, I'm going to use my nifty little box to do this because I like my box. I don't make mistakes. Actually, I want that box to be that big. Let's start over with the box. When I use the box, I don't miss terms and I don't make sign errors. So x times x is x squared minus x minus 3ix, negative x plus 1 plus 3i plus 3ix minus 3i minus 9i squared is plus 9. Okay. Those cancel each other out, and those cancel each other out, and I'm left with x squared minus 2x plus 10. These go together, and these go together. Now, my original coefficients were 1, negative 4, 14, negative 20. Hang on. I'm not that good. Minus 4 plus 14. And then plus 20? Yes. No, minus 20. And I'm going to divide this by x squared minus 2x plus 10. X squared goes into x cubed x times. This is x squared minus 2x squared plus 10x. And I'm going to subtract that whole thing. So this is negative 2x squared plus 4x, bring this down, minus 20. Negative 2x squared divided by x squared is negative 2. and this is negative 2x squared plus 4x minus 20, and that leaves me with 0. So there's my remaining factor. There's actually a third method to do this. I'm given x cubed minus 4x squared plus 14x minus 20 to begin with. And I know I have two complex solutions. That leaves me with one real solution. And it has to be rational. Right? Because all of my coefficients are rational. So irrational solutions, if you have, or irrational roots, if you have rational coefficients, also come in conjugate pairs, just like the complex roots do. So, and I can only have 3 roots. 2 of them have to be complex. So the other one has to be rational because I can't have a conjugate pair. I can only have 1. We already know that it's 2 because we've already solved this. But otherwise, you would take plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, etc. until you found it. 1, 2, negative 2, negative 4, 10, negative 20. And that leaves me with this quadratic. And I don't even need to solve this. Note that that quadratic is the same as this quadratic. But I already know that 1 plus or minus 3i are the other roots. So be sure you give all 3 when you state your answer.